As Terry Okita reports, not only are reservoirs running low, but underground resources are depleting at an alarming rate.
A groundbreaking study published in Nature in January 2025 has revealed something new about what's sitting beneath Yellowstone. And what scientists found is not what many people expected. For decades, we thought we understood the structure of Yellowstone's magma system. Two main reservoirs, a shallow chamber, a deeper recharge zone, a relatively straightforward vertical plumbing system. That model just changed. What researchers uncovered isn't bigger magma. It isn't hotter magma. It's something far more important. It's structure. And in volcanology, structure determines behavior. Using one of the densest seismic imaging campaigns ever deployed in a volcanic system, scientists reconstructed the most detailed 3D map ever created beneath Yellowstone. Thousands of earthquake waveforms. Machine learning enhanced tomography. Cross-validated velocity models. The kind of resolution that simply wasn't possible a decade ago. And what emerged from that imaging wasn't a single chamber. It was a broad, partially molten cap, a layer sitting just a few miles beneath the surface that appears to control how the entire volcanic system breathes. And that word matters. Breathes. Because Yellowstone doesn't sit still. It rises, it falls, it fractures, it releases steam, it generates earthquake swarms, it shifts subtly year after year. The question has always been, what mechanism regulates all of that? This study may have just provided the answer. Before we go further, let's address the immediate concern. Does this discovery mean Yellowstone is closer to erupting? No, but it does change how scientists interpret warning signs. For years, Yellowstone has been described as having two major magma reservoirs, a shallow rhyolitic body roughly 3 to 8 miles below ground, and a deeper basaltic reservoir between about 12 and 30 miles down, feeding heat upward from the mantle. That framework still holds, but what the January 2025 study revealed is a laterally extensive pancake-shaped magma cap between roughly 4 and 6 miles beneath the surface, directly within the depth range where many deformation signals originate. This cap isn't liquid lava sloshing around. It's partially molten rock. Melt fractions in some zones range from 15 to 25%, meaning most of the material is still solid, but enough melt exists to change how the rock behaves mechanically. That threshold is critical. Once melt exceeds roughly 10 to 15%, rock transitions from rigid to semi-ductile. It becomes compressible. It can store pressure. It can deform. It can transmit fluids. Think of it like a dense sponge infused with molten material. And that sponge may be what absorbs, spreads, and moderates pressure from deeper magma injections. Previous models imagined Yellowstone's magma body more like a vertical balloon. But the new imaging shows a flatter, interconnected network, sills and melt lenses extending laterally across the caldera. That geometry matters, because eruptions don't happen just because magma exists. They happen when magma becomes connected, pressurized, and mobile. Right now, connectivity remains limited, and that's reassuring. But here's where the study becomes even more interesting. For years, scientists have observed repeated uplift episodes, particularly near Norris Geyser Basin, ground rising inches over months, then subsiding, then rising again. Those deformation patterns didn't always perfectly match deeper magma models. Now they might. If gas and melt accumulate beneath this cap layer, pressure builds gradually. The cap flexes. The crust above it lifts. When fluids escape through hydrothermal systems, geysers, hot springs, fumaroles, pressure drops and the ground settles. In other words, Yellowstone may not be building toward eruption, it may be constantly self-regulating, and that's a completely different narrative. The study's lead authors suggest this cap acts as a transitional boundary between deeper basaltic injections and shallower rhyolitic storage zones. Magma doesn't surge straight upward, it spreads laterally, it intrudes slowly, it distributes heat across a wide area. That slow distribution could be one reason Yellowstone hasn't produced a major caldera-forming eruption in 640,000 years, and hasn't erupted lava in 70,000 years. But let's zoom out for a moment. Yellowstone is not dormant. It generates 1,000 to 3,000 earthquakes per year. It experiences measurable ground deformation. It vents massive amounts of heat, more than any other geothermal system in North America. The volcano is alive. The difference is that now we understand its architecture more clearly. And architecture determines risk. For a super eruption to occur, melt percentages would likely need to exceed 40 to 50% across a connected volume. The study found no evidence of that. The cap contains melt, but it's dispersed, fragmented, layered. There's no giant underground lake of lava waiting to burst. And that clarification matters. Because public perception often imagines Yellowstone as a ticking time bomb. The data paints a more nuanced picture. This system behaves like a long-term magmatic engine. Deep basalt rises slowly from mantle sources. Heat transfers upward. Melt accumulates incrementally. Pressure diffuses through hydrothermal pathways. That's not explosive instability. That's dynamic equilibrium. Still, equilibrium doesn't mean static. Could regional tectonic stress change the integrity of the cap? Possibly. Yellowstone sits within the broader basin and range extensional province, where crustal stretching continues today. Could deeper magma injections increase melt over thousands of years? Yes. But what this study tells us is that any large-scale change would likely unfold gradually, not suddenly. And that distinction is critical. One of the most powerful aspects of this discovery isn't what it revealed, it's what it ruled out. No signs of massive interconnected melt bodies primed for eruption, no evidence of runaway pressurization, no indicators of a near-term catastrophic event. Instead, scientists now have a high-resolution blueprint of Yellowstone's internal plumbing. That blueprint allows them to interpret earthquake swarms more accurately, to distinguish between hydrothermal fluid movement and magmatic intrusion, to model deformation events with greater confidence, and to reduce unnecessary alarm. But here's the hook that matters most. The better we image Yellowstone, the more we realize how complex it truly is. And complexity means surprises are still possible. Not catastrophic surprises, but scientific ones. Each improvement in seismic resolution peels back another layer of a system that has been evolving for over 2 million years. The January 2025 Nature study doesn't signal danger. It signals progress. It shows that what lies beneath Yellowstone is layered, buffered, and far more intricate than the simplified diagrams most of us grew up seeing. And in volcanology, understanding structure is the foundation of prediction. So should we be concerned? Concerned enough to keep monitoring? Absolutely. Concerned enough to expect an eruption tomorrow? No. Yellowstone remains one of the most heavily instrumented volcanic systems on Earth. GPS arrays, seismometers, satellite radar, gas sensors, continuous data streams analyzed in real time. If meaningful change begins, scientists will see it. What this discovery gives them is sharper vision. And sharper vision is the opposite of panic. The real story under Yellowstone isn't that something terrifying was discovered. It's that something hidden was clarified. And that clarity may be the most important breakthrough of all.